This is lesson 23, decomposition rules. Last lesson, we learned how to decompose double negations, conjunctions, and disjunctions in truth trees. We developed these three rules. For a double negation, or a negation of a negation, the negation of a negation is simply the proposition itself. For a conjunction, you decompose a conjunction by decomposing the two conjuncts with one right above the other. For a disjunction, disjunctions branch into two different disjunct branches. Then, for all of these, you check off the compound proposition after you've decomposed it into its literals. Now, today you need to learn how to decompose all 5 logical operators and their negations, because for our purposes, not only negation, conjunction, and disjunction, but also conditional and biconditional, and the negations of all 5 of them need to be decomposed. By doing so, you will derive all the necessary decomposition rules for truth trees, and we will be able to analyze any truth functional proposition using truth trees. Exciting. So let's take a look at the rule of negated conjunction. What has to be the case for not P and Q to be true? For not both P and Q to be true, P and Q has to be false. When's it false? Well, when either part is false. In other words, when not P is true or when not Q is true. If not P is true, then P is false. If P is false, then P and Q is false, and not false is true. For this whole proposition to be true, not P could be true, or for the whole proposition to be true, not Q could be true. So that's how you decompose a negated conjunction, and you can check it off. So that's the rule for a negated conjunction. Let's derive the rule for a negated disjunction next, not P or Q. What needs to be the case for a negated disjunction to be true? For it to be true, P or Q would have to be false. And when is a disjunction false? A disjunction is only false when both parts are false. So, for not P or Q to be true, not P has to be true and not Q has to be true. So, this is how we decompose a negated disjunction, with a not P right above a not Q. In other words, the negation of the first component above the negation of the second component in the negated disjunction. The last 2 rules could be derived from De Morgan's theorem. De Morgan's theorem says not both P and Q is equivalent to not P or Q. So we see the branching of the negated conjunction, and not P or Q is equivalent to not P and not Q, so we don't branch. It can help you to remember the decomposition rules by remembering De Morgan's theorem. Okay, so let's practice a little bit. We're going to use a truth tree to determine the consistency of this set of propositions. Not both P and Q, and neither P nor Q. Those are our set members. Now let's break down proposition number 2 first, because that's the one that doesn't branch. And that breaks down into the negation of the first proposition and the negation of the second proposition. Not P and not Q. For neither P nor Q to be true, not P is true and not Q is true. That's the rule for a negated disjunction. And we justified it from line 2 doing a negated disjunction decomposition. And then you check that off. Now there's no contradiction yet, so we continue to decompose, and we decompose the proposition that is still a compound proposition. By De Morgan's theorem, not both P and Q decomposes into not P or not Q. We label that as a negated conjunction decomposition from line 1. Now we look along the branches. Both branches are entirely decomposed. Isn't that great? Everything is either a literal or a checked off proposition. On the one branch we have not P, not Q, not P. No contradiction there. On the other, we have not P, not Q, not Q. There's no contradiction there. So this is a consistent set, and we can recover the truth values, our favorite part. Along the left branch, we have P is false and Q is false, and the exact same sort of thing along the right branch. And so those are both the truth values by which those propositions are true at the same time. That makes sense. For not both P and Q and not P or Q to be true, both propositions would have to be false. So I am not both a garbage collector and an astronaut, and I am neither a garbage collector nor an astronaut are both true, because it's false that I'm a garbage collector, and it's also false that I'm an astronaut. Let's use a truth tree to determine the consistency of this set next. This one's gonna be a bit bigger, a large tree, maybe giant redwood size. So set member number 1 is not P and Q. Set member number 2, not P or not R. And set member number 3 is Q or R. When you're setting this kind of thing up, you're going to want to make it wider put the justifications nice and far over, put the numbers nice and far over, because you're going to be doing some branching and you need to leave yourself plenty of room. You don't want your step numbers to start to get close to the propositions and to angle outward as if you need more room. We want a redwood, not a scraggly dead swamp tree. Okay. Which one do we decompose first? Well, little tip, start by decomposing the proposition that doesn't branch so that you have to write or draw as few propositions as possible. And the one that doesn't branch is number 2. So we do a negated disjunction decomposition. We negate the first proposition and then right below it we negate the second proposition, not P and not R. You can't skip the double negation and just call that an R. You need to follow the rules strictly. So, not P or not R decomposes into not P and not R, and we check that off because we decomposed it. Now, not R doesn't branch, and we can just decompose that one into R and check that off with the justification of 5 double negation decomposition. There we go. Quick check of not P and R. Nothing contradicts yet, so we can continue. Let's branch the first set member, not both, not P and Q. Remember, a negated conjunction branches, and it negates the first part and negates the second part. So we have a not P and a not Q here. Notice you might be confused into thinking the branches are coming from that R, but they're not. Look at the justification. They're coming from step 1. That's why the number 1 is there. Step 1 is now decomposed, and so we check it off. And then we see a not P that we can then decompose very quickly into a P using the double negation decomposition in line 7. Now we see a clear contradiction. We have a not P in number 4 and a P in number 8, and so 4 contradicts step 8, and we close that branch. Once you've closed the branch, you do not need to decompose off that branch any longer. You only decompose off of open branches. Now, we only have one open branch left, the right-hand side, and so the only proposition that has not been decomposed is Q or R. So we're going to branch Q or R off of that one open branch of the not Q. Q or R branches off into those two parts, Q and R, a disjunction decomposition from line 3. We check that off, and now we look along the branches. You should see a contradiction between line 7 and line 9. Not Q contradicts Q, so that new branch is closed immediately. But along this other branch, we have not Q, R twice, not P, and then checked off propositions. So that's an open branch. There's no contradiction there. So this is in fact a consistent set, and we can recover the truth values. P, Q, and R are 3 different constants for this set of propositions. In step 4, not P has to be true, so P has to be false. Step 6 and 9, we have R is true, so R is true. Step 7, we have not Q is true, so Q has to be false. In other words, false, false, true for our P, Q, and R. So for those 3 propositions to be true, the individual variables or constants would have to be those truth values. Okay, let's continue learning our decomposition rules. How about the rule of the conditional? How do we decompose if P then Q? Well, take a look at our familiar truth table for if P then Q. When is that conditional true? Well, when P is true and Q is true, when P is false and Q is true, or when they're both false. So you might think we have 3 different branches because there's 3 different ways for that conditional proposition to be true. But you can also think of it in another way. If P then Q is true when either P is false, the last 2 rows of the truth table, or when Q is true, the first and third rows of the truth table. So we can decompose if P then Q into not P or Q. That means if not P is true or Q is true, the whole proposition is true. After we check it off, you might recognize that this decomposition rule could also be derived from material implication from our formal proofs of validity. Remember that material implication said if P then Q is logically equivalent to not P or Q. So that's our decomposition rule for the conditional in another form. There are 2 ways you can reason to that. Pretty cool. Logic is cool. How about the biconditional? P if and only if Q. When is that true? Again, let's take a look at the defining truth table. The pattern for the biconditional is true, false, false, true. The biconditional is true when P and Q are both true or when P and Q are both false. Now that word or tells you that the biconditional truth tree is going to branch. And the biconditional is true when P and Q are both true, so we write a P above a Q, and because that's when P and Q are both true, and when P and Q are both false. That's the rule for the biconditional. You decompose the biconditional by branching and then putting the true component parts one above the other on one side, and then on the other branch, the negation of the two component parts, one above the other. So P if and only if Q branches out into P, Q, and not P, not Q. This rule could be derived from material equivalence, which says that P if and only if Q is equivalent to P and Q or not P and not Q. That will help you remember the decomposition rule for the biconditional. Moving on, how about the negated conditional and the negated biconditional? Not if P then Q. When is that negated conditional true? Not if P then Q is true when if P then Q is false. When is an if then false? Only when the antecedent is true and the consequent is false. So a negated conditional, not if P then Q, decomposes into P and not Q. If P is true and not Q is true, then not if P then Q is false. That's the rule for a negated conditional. You decompose them into their parts and you negate the consequent. Finally, the negated biconditional, not P if and only if Q. How does that one decompose? Again, we look at what the truth value of the component parts has to be for the whole proposition to be true. So let's look at the truth table for a negated biconditional. If the biconditional has a pattern of true, false, false, true, then the negated biconditional is false, true, true, false. So when is the negated biconditional true? It's true when P is true and when Q is false, or when P is false and Q is true, those two middle rows for the truth table. So the negated biconditional, not P if and only if Q, decomposes into P and not Q, or not P and Q. Take a moment to think about what we're doing right now. With the negated biconditional, we branch and it's either the first proposition and the negation of the second, or the negation of the first proposition and then the second. That's the rule for a negated biconditional. Now we get to practice using a truth tree to determine the consistency of this set. Are they consistent? If so, for what truth values of P and Q? Our first set member is not if P then Q. Our second set member is if Q then P. The not if P then Q doesn't branch, so we should decompose that one first. And the rule for the decomposition of a conditional is the first proposition and the negation of the second proposition. Not if P then Q is true, when P is true and Q is false, and we justify that as a negated conditional decomposition. We check the proposition off in line 1 as well. There we go. Now we decompose proposition 2, if Q then P, into not Q or P. Remember material implication. If then is equivalent to not or. So if Q then P decomposes into not Q or P, then we can check that off. Now everything is decomposed into its literals. We follow the not Q branch. No contradiction there, so that's an open branch. We write an O. We looked at the other branch and no contradictions there, so that's also an open branch, another O. So this is a consistent set and we can recover the truth values. Here we have P is true and Q is false, and then here P is true and Q is false. So for both of those propositions to be true, P would have to be true, Q would have to be false. I'd encourage you at this point to pause the video and do a truth table for these two propositions as well, and you'd see that the truth table would also show that these two propositions are true when P is true and Q is false. I'm waiting. Aren't you going to pause it? Okay, we're going to practice one more time. Use a truth tree to determine the consistency of this set. Aha! 3 propositions. 3 set members. Make sure you've got space on your paper. Not P if and only if Q, Q if and only if R, and not P. Remember, we're asking what do the values of P, Q, and R have to be for these 3 propositions in the set to be true. Let's start off with number 1 there. We decompose a negated biconditional into P, not Q, or not P, Q. It branches into the first one and the negation of the second, or the negation of the first one and then the second. And then we check that off because we've decomposed it. And now we see a contradiction already. Line 3 already contradicts with 4. P contradicts not P, of course. So we close that left-hand branch. Good work. But there's no contradiction on the right-hand branch, so we continue to decompose off of that branch. A biconditional decomposes into the 2 propositions, one above the other, or, on the negated branch, the negation of the 2 propositions. Q if and only if R decomposes into Q and R, or not Q and not R. We label that as 2 biconditional decomposition, and we check that off. Now we see a contradiction on this branch, the right one. Line 5 contradicts line 6, so we can close that branch. But there's no contradiction along the left branch. Everything is decomposed into literals or checked off propositions, and so we have an open branch, and we can recognize that these propositions are consistent and move on to recovering the truth values. We have P is false, Q is true, R is true. So the truth values of the component parts when all three of the propositions are true is false, true, true. Let's summarize this particular lesson. A truth tree decomposition rule can be developed for any compound proposition. To do so, the truth values for the variables or constants must be determined such that the proposition is true. This has been done for conjunction, disjunction, conditional, biconditional, their negations, and double negation. That's all we need. Those are all the different types of propositions that we can have in propositional logic. Good for us. Pat yourself on the back. The decomposition rules are listed in Appendix C in the back of your book, so get familiar with those rules. They're like the rules of replacement and inference for formal proofs of validity. Exercise 23 is going to help you get really familiar with them. You're just going to be using truth trees to determine the consistency of a set of propositions. The first 4 problems each give you practice with the different rules of truth tree decomposition, and those go pretty quickly. 5 and 6, a little more complicated. Start by giving yourself plenty of room when you decompose those propositions. Put the line number off to one side, put the set member or the justification off to the other side. Give yourself plenty of width. Take number 5, for example. When we decompose that first proposition, we decompose the conditional first. That would decompose into not J or not J if and only if K, and so on. So remember to check off any proposition that you decompose as you go, and remember to check the branches to see if they close with contradictions. If they have any open branch, the truth tree is consistent, and you can recover those truth values. Dive on into those exercises. On the wall behind me, you can see the 50 adorable fallacies from the amazing Dr. Ransom's Bestiary of Adorable Fallacies. This is the informal fallacy book that all of your family is going to love reading together. Second book I wanted to show you is a book written just for classical homeschoolers, Classical Me, Classical Thee, Squander Not Thine Education. This book explains why you have to do all the classes you're trying to do. So please remember to subscribe and hit the bell. You can check the links below in the description for these 2 books and anything else from Logos Press. Thanks for watching.